Hi everyone, I am Nandan Roy. First of all, I would like to thank the organizer for giving me this opportunity to present my work in this Cosmology from Home 2023. I will be talking on interacting dark sectors from a dynamical system perspective. So before I start, let us discuss about the state of the art in cosmology and in dark energy sectors that we know from the discovery of from the supernova in 1998 that our universe is not only expanding, it is expanding with acceleration. And lambda CDM model has been the most successful model in explaining the accelerated expansion. But even though it is immensely successful in explaining the accelerated expansion of the universe, but it suffers from some problems coming from both theoretical and observational point of view. From the theoretical point of view, it suffers from the famous cosmological constant problem and cosmic coincidence problem and other also some other problems. But very recently, there is a mismatch in measurement of the cosmological parameter from the late time data and early time data, which put the cosmological constant in another challenge. So the most famous tension recently is the Hubble tension, in which there is almost more than 5 sigma tension between the measurement of early time measurement of Hubble tension from the early time data like the CMB data and the late time data like the distance ladder measurement. So in this figure, you can see that the blue lines are the measurement from the CMB data, which and the blue lines are the distance ladder data, and the red lines are the CMB data. So as over the years, our precisions in measurement increase. So at this moment, they are almost about more than 5 sigma in tension. So which put that lambda CDM in challenge, because for the CMB data, we consider the lambda CDM as the model, the accelerated expansion of the universe. And similar to the Hubble tension, there is another tension is the sigma in the measurement of sigma, in which the measurement of sigma from the Planck data is in tension with the weak lensing data and Z6 survey data. So this tension is not as big as the Hubble tension, but it is statistically significant. So all these things inspire the cosmologists to think beyond the lambda CDM model as something beyond the lambda CDM model to explain the dark energy. So the second popular choice is the scalar field as the dark energy, and in which actually people consider both minimally and non-minimally coupled scalar field. Here we will be considering minimally coupled scalar field. In our setup, we will consider that the both phantom and the quintessence scalar field are incorporated in a single setup. So here, once we use the Lagrangian, we can find out the field equations which are of these forms, and this sigma is the switch parameter. If sigma, this epsilon is the switch parameter. If epsilon is +1, this is quintessence field, and if it is minus, then this describes the phantom field. And both the rho phi and p phi, the energy density and pressure density for the scalar field, can be written in this form with the epsilon parameter. So now for this work, we have considered the interaction between the dark sectors, that is dark energy and dark matter, and here we have the interaction term Q, and the Q actually can be function of anything, and as you can see, these two densities, they are not separately conserved, but they are conserved as a total. If you sum them up, they are conserved. And the Klein-Gordon equation for the scalar field also modified because of this interaction term in this form. So now, as I mentioned in the title, that we want to study these interacting models from the dynamical system perspective. So let us discuss about what is dynamical system analysis. Dynamical system analysis is a like a model which describes the temporal evolution of a system, and it is a mathematical tool to understand the qualitative behavior of a nonlinear system without finding an exact solution. And dynamical system now has been used in many areas of science and engineering, and cosmology. In cosmology, dynamical system analysis has been widely used. So there are a few steps for dynamical system analysis. So first, one has to write the system as a set of autonomous equations. Then as a next step, one has to find the fixed point of the system. Then the next step, one has to find the Jacobian matrix of this f of x at that fixed point. Then from that, one needs to find the eigenvalues of the Jacobian matrix, and from the sign or the signature of the eigenvalues, one can find that if some fixed point is stable or not. And why these fixed points are important? Because fixed point describe the origin or attractor for some particular solution. So this fixed point can work as a beginning and the ultimate fate of the universe. So knowing this for a particular model is very important from the cosmological point of view. So as I mentioned, we have to write down the system as an autonomous equation. So for that, we introduce this following setup. Transformation of variables, and with this transformation of variable, one can write the Friedman equations in this form. Here, the f of xy is the interaction term, and gamma is the related to the potential. And one can also write all the cosmological parameters in terms of these xy variables. So now as we want to study this system, one can see this set of equation is not closed. We need to find we need to supply some form of the potential, hence the gamma. So what we did here, we look at the last equation, which is lambda prime, and for the finding the fixed point, we choose two different class. So that you can see for the fixed point, we have to make this one 0 and find the solution. So there are two classes, either gamma equal to 1 or gamma equal to 1. If gamma equal to 1, this is the exponential potential case. If gamma is not equal to 1, so this is a non-exponential potential case. So we choose these two cases separately and study their phase space behavior. And for the exponential potential, we choose the gamma equal to 1. So that means the lambda is a constant. So essentially, the system is a two-dimensional system. And we find the fixed point of this system. This is Q1, Q2, and Q3. So these are the class of fixed points, since we have not considered any form of the interaction f of xy. So one has to, suppose for this Q2, one has to solve this quadratic equation to find the exact fixed point for this f of x, any chosen value of f of x and 0 xy. So, but these are the three classes, and one can study the stability of these fixed points even for an arbitrary potential. And here we can see that for Q1, this is a completely x equal to 0, y equal to 0, means it's a completely matter-dominant fixed point, and this is the eigenvalue, and one eigenvalue is positive. So that means this fixed point is definitely unstable fixed point, and this one, the Q2, this is the eigenvalue, and one can see with this eigenvalue that This could be either stable, unstable, or settle, because these two functions cannot be negative simultaneously. And Q3 actually depends on the choice of f of xy. So for a two-dimensional system, one can study the sign of the eigenvalue form, the trace, and determine it. So we can study the stability of this system for a arbitrary choice of interaction and exponential potential. Now let us move to the non-exponential class of potentials. The system becomes a 3D system as their lambda is no more constant, and these are the fixed point one can find. And each fixed point has different property, cosmological property. And like P1 is matter-dominated fixed point, it is the unstable one, as this is the eigenvalues. One eigenvalue is positive, so P2 does not exist for the phantom case. Only quintessence can have this one, and this is also an unstable fixed point. And P3, one needs to find P3 for more analysis, because P3 is a non-hyperbolic fixed point. So there is one eigenvalue which is 0. So this is a non-hyperbolic fixed point. So one need to further investigate these P3 and P4, because they comes with the 0 eigenvalues, and other eigenvalues can be negative. So for further investigation, we consider a particular form of the interaction, which is f of x, y equal to alpha. And this form, so for different choices of alpha, m, and gamma, you can include a large class of potentials for interactions in the given used in the literature. So for the exponential potential, this is the phase plot for different choice of lambda. So we choose lambda equal to -1, 0, and +1. So as lambda is constant for the exponential potential, and this circle gives the Friedmann constant. And one can see that the solution started from some dark energy dominated era, and it's going to the dark energy dominated era again. So here is one that the solutions actually started from dark energy dominations and passes to matter domination. One has to remember that here we have not considered the radiation in picture. So when at the early time the matter is not dominating, so at that time to close the Friedmann equation, the scalar field was giving kind of a proxy to the radiation, and it can be studied that even this is a radiation scalar field dominated phase, but the equation of state is positive. So it was working, the scalar field was giving proxy as radiation. So one can then one can do it for the phantom case, and you can see this hyperbola. It comes from this constant that -x² plus y² is between 0 to 1. This is the Friedmann constant, and one can easily see that this is showing the similar behavior as the quintessence case. Now we plotted the cosmological parameters for the exponential potential for the quintessence case, and one can see this is the omega m and omega phi, and most interestingly, this is the interaction evolution of the interaction term. So what we did here for this, actually, we consider the value of the current value of for the numerical evolution. We consider the current value of the x0 and y0 from the value or current value of the omega phi 0 and q0. And one can solve these two equations to get some present value of x0 and y0. And then one can actually solve this in the autonomous system and get these cosmological parameters. And this plot shows that the comparison with data, which shows that this interaction actually can match at late time the data very well. And the last plot here shows the evolution of the interaction term itself. It started from some non-zero value, and it goes to be going to be 0 in future. So, but at present, it could have some non-zero value. So we perform the same analysis for the phantom case, and it gives the similar result to the quintessence, and the difference is in the equation of state. It becomes from -2 less than -1 to -1, which was for quintessence. This was greater than -1 to -1, and it has the similar feature to the quintessence case. And for the non-exponential case, we have two different class of potentials by choosing two different form of gamma, because gamma could be function of lambda. And once we choose this gamma equal to half, and this will have these two different forms of the potential. One is power law and another is cos hyperbolic. And these are the phase plot for the two cases. For the gamma equal to half case, for the quintessence, and this is for the phantom, and this cylinder shows the treatment constraint because we have a third dimension, so it becomes a cylinder. For this one, it shows the hyperbolic surface, and as it is expected, the universe is going to be dark energy dominated in future, and it passes through a matter domination, which is a saddle in nature. So we use the similar technique to investigate the numerical evolution, and we find the existence of non-zero interaction at present, and which is going to be zero in future. And this is for the phantom case. We have the similar result for the phantom case. So now we have the gamma equal to this other case, and we plot the phase plot. It almost remarkably similar to the previous case, and the cosmological parameter shows the similar behavior. So, and also for the phantom case. And as a conclusion, we have studied the interacting scalar field model, including both phantom and quintessence, in a single setup with a very general kind of consideration of the interaction term. And we use dynamical system analysis, and our finding shows that there could be interaction at present, which is going to be zero at future, and yeah. And our choice of interaction is quite general. So I hope you like the work, and thank you for your attention.